Okay.
So I'd like to introduce today's speaker, Professor Ryo Fujita, who's going to give us a talk titled Singularities of R-matrices and E-invariants for Dynkin quivers. So thank you, Professor Fujita, for accepting the invitation, and you can start whenever you're ready.
Yeah. Thank you very much for the invitation. And yes, first of all, I'd like to express my gratitude to the organizers for giving me this opportunity to speak. So yes, so so let me. So today I'd like to explain something about singularity of R matrix. So this is uh, about the representation theory of quantum group, and my goal is to connect this thing with another representation theory, which is about that of Dynkin quivers. So let me try to first explain the motivation of this talk. Motivation from the quantum group side. So the setting is the following. So we start with simple algebra, finite-dimensional complex simple algebra, and it is well known that this is classified by the Dynkin diagrams. And since we are going to work with quantum group, we fix a quantum parameter. So this is a certain complex number, and we assume that this is not this is non-zero, and its multiplicative order is infinite. So it is not a rootability in this talk. And associated to uh, this data, we can attach so-called quantum loop algebra. So this is the main player in this talk. So what's this? So this is I do not give a precise definition, but roughly speaking, this is a deformation, certain deformation of the Hopf algebra structure of the universal enveloping algebra of the loop Lie algebra. So loop Lie algebra LG here is just a extension of coefficients to the ring of Laurent polynomials in the variable, additional variable z, and we think this Lie algebra as a Lie algebra over the field of complex numbers. So this is an infinite dimensional Lie algebra, and we take its universal enveloping algebra over C. And so this is a kind of affine quantum group, and and we consider its category of finite dimensional modules. So because uh, our quantum loop algebra is a Hopf algebra, so this category has the structure of C-linear monoidal abelian category. And yes, so and this category is the main object of study in this talk. And actually, this is very interesting monoidal abelian category. And so one of its features is the following. So this category is, of course, monoidal category, but this is not braided tensor category. And in particular, actually, in this category, we can find many interesting pairs of simple representations, such that they don't commute. So the tensor, if we swap the ordering of tensor structure, they may not be isomorphic. So this is an important feature of this category.
Excuse
But,
me.
yes,
Sorry.
sure.
Could you recall, please, the multiplication? Maybe it's simple and I don't remember. The multiplication of LG as the
Multiplication.
algebra?
Yes, okay, yes. So this is very simple. Sorry. Okay, sure. So this is LG and the Lie bracket between this kind of element. So X and Y are the elements in the ordinary algebra. G and F and Fz and Gz are Laurent polynomials. Then this Lie bracket is, first we just take Lie bracket of X and Y and Fg are just multiplied.
I
So
see.
this is a, yes. So this is a loop algebra, yes. Loop
So
algebra.
the scalars are the functions. Okay.
Yes. So this is just a scalar extension. Yes.
Okay. Thank you.
Yeah, but clearly this is infinite-dimensional algebra, right? Yes. Okay.
Great.
Okay. Thank you for the question, and please feel free to interrupt me if you have anytime you have any questions. So, okay, good. Then, so this category is not commutative in this sense, but but interestingly, we can say that this category is generically braided. Generically braided in the following sense. So working with this quantum affine or quantum loop algebra, there is a freedom of additional freedom of deforming modules. So we first deform each module L with certain continuous parameter, which is usually referred to as spectral parameter, and we take this Z to be generic spectral parameter. So this is a certain deformation. And this Z is actually comes from this loop, yes, the loop variable Z. And so this is certain deformation. And if we specialize this Z equal to 1, then we recover the original module. And once we apply this kind of deformation, everything will be commutative. So the tensor product deformed L times L prime is now isomorphic to the opposite product. Okay. And moreover, if we fix
But this
generating
LZ
vector,
is not necessarily irreducible anymore. It's not simple, or is it?
yeah, this is simple. Actually, this is
Still simple.
Yes, still simple. And if we fix highest weight vector, so this is certain special kind of cyclic vector in modules. And we can normalize this isomorphism to send this tensor product of highest weight vector to the opposite tensor product of highest weight vector. Then this isomorphism uniquely determined. And this is what is called R-matrix, or more precisely, the normalized R-matrix. So this is actually depending on, yes, depending on that, and yes, called normalized. R matrix. And we can see this as a matrix valued rational function, actually. So this can be seen as a rational function in Z valued at this linear space. This is finite-dimensional linear space, and if we fix the a basis of the modules, then we can identify this space as a space of matrices. So in this sense, this R matrix can be seen as a matrix valued rational function. So it makes sense to consider the singularity of this R matrix, and we are, in particular, we are interested in the singularity of this R matrix at Z equal 1. So I define certain invariant O of L prime to be the pole order of this R matrix at Z is equal to 1. So this is a certain non-negative integer by definition. And actually, this is very important numerical invariant in the representation theory of quantum loop algebra. So to see it, let me show you the simplest example. In the case V is equal to type A1 SL2. And in this case, we have a algebra homomorphism from quantum loop algebra to the quantum group of SL2. So this is called evaluation homomorphism. So for each non-zero complex number A, we have this evaluation. And so by using this algebra homomorphism, we can construct irreducible representation of quantum loop algebra just by pullback. So for example, this quantum loop, this quantum SL2, quantum group SL2 has the natural vector representation. And we can pull back this representation to get an irreducible representation of quantum loop algebra. So we define a representation LA to be this pullback. So this is something called the fundamental module. Of quantum loop algebra. And we can compute the R matrix between fundamental representations explicitly. So let me see. So I already prepared this. So this is the, let me put here. Yes. Yes. It's just visible. Yes. Okay. Yes, good. So we are now considering the R matrix between L of A and L of B. So it is now the rational function valued at 4x4 square matrix. And the explicit computation gives us this answer for the R matrix. And we find that, therefore, O of LA and LB in this case So it only have, so the denominator is given by this number. So so C is the ratio between B and A. So therefore it only has at most a simple pole at z is equal to 1 if this number C is equal to Q square. So when B is equal to A times Q square, and otherwise the z is equal to 1 is a regular point. So it's just 0. Okay. And when the R matrix has a singularity at z is equal to 0, sorry, z is equal to 1, then what happens? So let us consider the case when this ratio is not Q square nor its inverse. Then we find that the corresponding tensor product, LA tensor LB, is now isomorphic to LB tensor LA. And this isomorphism is given by the specialized R matrix because there is no singularity here, so we can always specialize. And for the inverse direction, we can also specialize. So this is this gives an isomorphism between them. And moreover, we can also prove that this tensor product is irreducible in this case. Yes. So this is the generic situation. But when the R matrix has some singularity, then some interesting phenomenon happen. So when it is not a case, so let us, for example, consider the tensor product LA tensor L of A times Q square. Then we cannot specialize the R matrix anymore because it has a pole, simple pole. But we can still specialize it once we multiply z minus 1 to it. Then so this cancel out the denominator in this case. So there's no singularity, so we can specialize it. But this homomorphism, so we get a non-zero homomorphism. But this homomorphism is no longer isomorphism. So it has an image, a proper image here, and we can see that this is one-dimensional trivial representation. So it has a one-dimensional image, and its kernel is three-dimensional. So kernel K is three-dimensional, and we can also prove that this three-dimensional kernel is actually another evaluation pullback of three-dimensional representation of UTXL2. And interestingly, the co-kernel of this image is actually isomorphic to K, the kernel of the other side. And we can also prove that the short exact sequence appearing here is non-splitting. This is non-split short exact sequence. And the other side is also non-split. And therefore, we can prove that in this case, this tensor product is no longer isomorphic to the opposite tensor product. So the commutativity breaks down in this case, at the singularity point. Yes. Okay, so this is the situation. Yes. But as I already commented, interestingly, in any case, so we have an equality. So So at a singular point, they are no longer commutative, but that if we consider Jordan-Hilda multiplicity, it's still the same. So in other words, we have the equality at the level of Grothendieck group. Yes. And in this case, in our case, we are working with monoidal category. So the Grothendieck group has a natural structure of ring. So we can say that this is Grothendieck ring. So at the level of Grothendieck ring, we always have commutativity. Okay, and this phenomenon is actually a general phenomenon. And so in fact, Edward Frenkel and Reshetikhin proved that the Grothendieck ring is a commutative ring. For any simple algebra G. So we see this phenomenon in SLT, but this can generalize to any G. And with this proposition, let me introduce the following terminology. So let us consider two simple representations. Then we say that they strongly commute. If the tensor product L and L prime is irreducible. This is this station is called strongly commutative because this implies that L and L prime commute actually, thanks to the proposition. Okay. And we also say that a simple representation is real if it strongly commutes with itself. So its tensor square is irreducible again. In this situation, we say that L is real. And with these terminologies, I can now explain the following theorem due to Kashiwara. Sorry. Kan Kashiwara. Kim and O. So which said that the singularity of R matrix actually measures the commutativity between simple representations in a precise sense. So assume that given two simple representations are both real, then the following statements are mutually equivalent. First statement is that L and L prime strongly commute. And interestingly, for real modules, this strong commutativity is actually equivalent to the commutativity. And these conditions are actually equivalent to the regularity of corresponding R matrix, namely the O between L and L prime vanish in the both direction, both orderings. So this is the precise meaning that this singularity of R matrix, so this measures the commutativity or non-commutativity. Between L and L prime. So thus, this number is very important invariant in the representation theory of quantum group algebras. But unfortunately, this is hard to compute in general. And the known cases, we have, of course, some known cases, but it's only for fundamental modules. Or something called Kirillov-Reshetikhin modules. And the goal of this talk is to compute this number O of L and L prime for more families of representations. More precisely, my goal is to describe this number in a certain monoidal subcategory called level 1 subcategory, which I will explain in the following section. But in a single word, this is very nice subcategory, which monoidally categorify across the algebra of type, of finite type 3. And using this monoidal categorification fact, I will describe this singularity of R-matrix in a satisfactory way for this monoidal subcategory. So this is the goal of my talk. So is there any questions so far? This is the end of the motivation part.
No, this is very clear. Yeah.
Okay,
So
thank you very much.
yeah, actually, I do have a question. So it is for types simple laced only, or for all thinking types?
So for this talk, this is only for simple laced type. So
Okay.
type ADE, yes. So from
ADE.
now on, we will restrict our attention to ADE,
Perfect.
unfortunately, but yes.
Yeah.
Okay. Any other questions? If not, let me try to explain what is level 1 subcategory in a precise way. So level 1 subcategory. So to define it, we need to recall the highest weight classification of irreducible representations, which is due to Shari and Wesley. So there is some very nice classification of simple representation in terms of highest weight classification. So according to this theorem, the irreducible representations in our category C is in bijection with so-called Drinfeld polynomials, but we can say it in the following way. So we consider the freely generated commutative monoid. Let me see. So we consider the commutative monoid generated by the symbols pi of I and A. And here I is labeled by the Dynkin node. Of our simple algebra. And A is non-zero complex number. So for example, in type A1 situation, SL2 situation, this pi of IA correspond to the simple representation, which is pulled back along this evaluation homomorphism of the fundamental representation. So this is, yes, like this. Okay. Let me
So
sorry,
in the
sorry,
language,
I forgot.
so
So this is type AN.
right.
Yeah.
So in the language of quivers, I would be the number of vertices of the quiver.
Yes. This
Perfect.
I is the vertex set of the Dynkin quiver.
Yeah.
But for
Yeah.
type AD,
Yeah.
so from now on, yes. So we will be working with quiver. So we assume that G is of type AD. So, sorry, ADE. And we can now define the level 1 subcategory. So this level 1 subcategory depends on the choice of a certain function on the set of Dynkin node. So this is which is called height function. So height function is an integer valued function on the set of Dynkin nodes, which satisfies the condition that the values the difference of the function between adjacent nodes. So in the situation, so I and J are adjacent in the Dynkin diagram, then the difference should be 1 in the absolute value. So this is the condition for this function psi to be height function. And so we can choose any such height function. Then we attach a cell subcategory of our category C, whose set of irreducible representations is parameterized by certain sub-monoid of this highest weight classification. So we consider some specific form of this pi of IA, where A is certain power of our quantum parameter Q, and this exponent is given by this height function or height function plus 2. So this is the definition of, so this category is called level 1. Level 1 subcategory. And similarly, we can define level L category for any positive integer L, but we are only considering this level 1 case.
So for the level L, it would be that you take K between 0 and L? Or...
Yes, exactly, yes.
Okay.
And it turns out that this category is monoidal subcategory. So it is closed under tensor product. Sorry, I forgot to mention that this definition of level L category is due to Hernandez-Leclerc. Okay, and this is a very, very good subcategory because it gives a monoidal categorification of cluster algebra. So let me explain this part. So this category is depending on the choice of height function. And on the other hand, we can attach for each height function a Dynkin quiver. So Dynkin quiver is just an orientation on our Dynkin diagram of G. And so we have to determine the orientation for each edge of our Dynkin diagram. For example, this edge between I and J. And we determine the orientation according to our height function. So namely, if psi of I is smaller than psi of J, then we orient this edge in this way from J to I. Yes, this is very simple. Yes. So this is Dynkin quiver, and we enlarge this Dynkin quiver a little bit to obtain an ice quiver. So ice quiver is just a quiver with specified frozen node. And in this case, so for underlying quiver, we consider our Dynkin quiver plus some additional frozen nodes for each original Dynkin node. And we put arrow from frozen to the corresponding Dynkin node. So from I prime to I for each I. And we also add arrow from non-frozen to frozen, which is oriented in the opposite way to the original Dynkin quiver, the original orientation. So in this way, we get certain ice quiver, which enlarges Dynkin quiver to psi. Yes. And attached to each ice quiver, we can define the corresponding cluster algebra of geometric type. So I will not explain anything about cluster algebra, but I suppose that you are familiar with this notion. So this is a certain commutative ring inside the field of rational functions in the initial cluster variables and generated by all the cluster variables obtained from initial ones by applying mutation. So certain combinatorial procedure. Okay.
Yeah.
Anyway,
Sorry,
so
and I would ask
okay.
you a question about the cluster algebra itself. So you are getting some coefficients here. Are these the universal coefficients or not necessarily?
So this is cluster algebra of geometric type. So the coefficient, yeah, how to say coefficients are given by frozen variables.
Yes.
Yes. So in this situation, let me see. So this is a subalgebra. By definition, this is subalgebra of field of rational functions generated by
Right.
xi and xi prime, and I is in a set of Dynkin node. And this is frozen variables. So this is frozen variables. And we mutate only unfrozen
Right.
variable.
Yeah.
Okay, good.
Yeah. No, I think, yeah, because doesn't matter.
okay.
I can ask you later.
Okay, good. Thank you. And now I would like to state the monoidal categorification theorem in this context. This is due to many people, started from Hernandez-Leclerc, and also Nakajima. And the most general result was obtained by Kimura and Chin, which said that for any choice of height function, we have an isomorphism between the Grothendieck ring of the corresponding level 1 subcategory and the cluster algebra we just introduced. This is ring isomorphism. So the Grothendieck ring was a commutative ring, so it makes sense, I think. And actually, this isomorphism is given by something called the truncated two-character. Which I do not explain in detail, but there is a notion of character in affine quantum group setting, which is called two-character. And if we consider a certain truncated version of this two-character, then this will give us isomorphism between Grothendieck ring and cluster algebra. So what I want to say here is that just this ring isomorphism is given in very natural way. So this is not an artificial isomorphism, but this is given by given in a natural way, and it has some representation theoretic meaning. Okay, and moreover, this isomorphism actually identifies the basis for both sides. So in the Grothendieck ring, on the Grothendieck ring side, there is a natural basis formed by the isomorphism classes of simple object by definition. And on the other hand, on the right-hand side, we have the basis formed by cluster monomials. So here, so in general, the set of cluster monomials is just a linearly independent set. It is not necessarily a basis of cluster algebra, but in our situation, it gives a basis because our cluster algebra is finite type. And this isomorphism actually identifies these bases. And in particular, if we consider the subset formed by cluster variables, then it corresponds to the so-called prime representation. So just prime means that it doesn't have any non-trivial tensor factorization. So this corresponds to the set of cluster variables under this isomorphism. So this is the meaning of the monoidal categorification. And this is available for any height function. And as a corollary of this fact, I think this is very important, that any simple representation in this level 1 subcategory is real. So this is because that cluster monomial, a cluster monomial is by definition that, satisfies a property that the square of cluster monomial is again a cluster monomial. And under this monoidal categorification result, this property is precisely translated to the fact that the simple representation is actually, all the simple representation are real. Okay. Yes. So we can freely apply the theorem of Kankashwara-Kim-O, which I mentioned before, which claims that the commutativity of simple representations are the equivalent to the regularity of the corresponding R-matrices. Okay, so this is a story about monoidal categorification. And for our main result, we need another kind of categorification of the same cluster algebra, which is called additive categorification. And this categorification is totally different in nature from monoidal one, and given by representational theory of quivers categorification. So let me explain this notion. So let Q be a general quiver, finite quiver, and we are working with so-called decorated representation. Of Q. So this is a pair. M and B, and here M is a genuine usual representation of the quiver Q. And we assume that this is finite dimensional representation, so finite dimensional representation of our quiver. And V here is just a bunch of vector spaces. So more precisely, this is Q0 graded vector space. So this is again finite dimensional. So Q0 is just a set of vertices. Okay, so such a pair is called the decorated representation. And I said this category to be a category decorated representation, so I use this kind of symbol. And for two decorated representations, M and M prime, we introduce the so-called E-invariant between them. So E of M and M prime to be the following vector space. So we take the usual X1 first extension group between the quiver representations M and M prime. And we add to this X1 a bunch of home spaces from Mi to Pi prime. M is quiver representation. So it has underlying Q0 graded vector space. So for each I, we have ith component. So this in terms of path algebra, this is EIM. And we just consider the linear maps, the space of linear maps from MI to VI prime. This is E-invariants. So this is finite-dimensional C vector space, just. And this is an analog of X1 for decorated representation. And we say that a decorated representation M is rigid if the invariant between M and itself vanishes. So this is this condition is analogous to the vanishing of self-extension between. Okay. And with these terminologies, I can state the additive categorification of a finite type cluster algebra. Yeah, I think there are several versions of additive categorification result, but my version here is due to Calder-Chapoton and also the XM Feynman-Zelensky in more general setting. Which says the following. So I state this theorem in a convenient way to our purpose. So we now come back to our original setting with type ADE simply algebra, and we take a height function on ADE thinking diagram. And for each choice, for any choice of this height function, there is a map, something called cluster character map. I'll write it CC. So this is from the set of objects in the category of decorated representation of our Dynkin quiver attached to disk psi. And actually it is a set of isomorphism classes. And from this set to the cluster algebra attached to our arXiv to Tilda satisfying the following properties. The first property is that this is so this cluster character map behaves like exponential map, so which takes sum of decorated representations, direct sum of representation to the product of their cluster characters. Okay, for any M and N prime. And secondly, so this map induces, if we restrict it to the set of rigid isomorphism classes, then it induces a bijection between this set and the set of cluster monomials. but without frozen factors. And in particular, if we consider the subset of cluster variables, but unfrozen cluster variables, then it induces a bijection between this set and the set of indecomposable objects. Indecomposable. Because of the first property of this cluster character. Okay. So for my purpose, it is enough to say these properties to have these properties. I think there's another version of additive categorization which claims more deeper properties of this kind of thing. Yeah, in terms of local cluster category or something like that. But for my purpose, it's enough to have these properties. Okay. So here is a simple consequence of this categorification result. So suppose that we have a cluster variables x and x prime. Then the additive categorification theorem said that there is an indecomposable decorated representation in and n prime, which correspond to x and x prime respectively under this cluster character map. Then in this situation, the following properties are mutually equivalent. So the first property is that x and x prime belong to a common cluster. So I do not explain the cluster, but this is equivalent to say that the product x prime is a cluster monomial. Okay, so this condition is actually equivalent to say that the E-invariant between m and n prime vanishes in both directions. So because this is equivalent to that, the direct sum of m and n prime is digit. Okay, because m and n prime are legit by this assumption. So okay, does it make sense for you? So this is a simple sequence of additive categorification result, and I'd like to compare this with monoidal categorification situation. So in the monoidal categorification, we have a corresponding simple representation L and n prime to the given cluster variables, whose truncated character is equal to the given x and x prime. And in this situation, the above two properties are equivalent to the condition of vanishing of O invariant monoidal side. Because this is equivalent to L and L prime strongly commute. As due to Kankashira-Kimov theorem. So I mentioned before. Okay, so let me recall. Yes, so this theorem, due to this theorem, this is equivalent to this, and this in terms of cluster algebra, this is equivalent to x and x prime belong to a common cluster. So having this remark, it seems to be natural to compare E-invariant and O-invariant. E-invariant in additive side and O-invariant on the other side. And this is the main result. So which is very simple now. So for any simple representations in our level 1 subcategory, the O invariant between them is actually equal to the dimension of E invariant of the corresponding rigid decorated representation of Dynkin quivers. So where M and M prime are decorated representation of our Dynkin quiver attached to the height function, which is rigid, and the cluster character of M is equal to the truncated Q character of L, and the cluster character of M prime is equal to the truncated Q character of L prime up to frozen factors. Yes. As I said that this O invariant is very difficult, very hard to compute in general. But I think the right-hand side, this E invariant is much easier to compute. Yeah, I would say much easier to compute. So I think this equality between O invariant and dimension of E invariant will give us a satisfactory description of left-hand side in terms of, yes, decorated representation. So this is the main theorem of my talk. Okay, I think the time is already used out, so run out. So I stop here. Thank you very much for your attention.
Thank you very much. That was quite nice. Are there any questions?
Thank you.
Thank you very much, Rio. I mean, it's a very beautiful result, really. I mean,
Thank you.
this really sort of highlights the deep connections that the cluster algebras are bringing to the theory somehow, right? I mean, there are all these different things around, and then they all try to categorify the same thing, and so this should be a bridge. And yeah,
I think it's interesting to compare the additive categorification and monoidal categorification because they are very different in nature. So comparing them is very non-trivial, I think.
This is very beautiful. And actually, I wanted to ask you a question about E-invariants. So lately there have been people trying to understand E-invariants in a more like in a sense the Dersenk-Beyman-Solevinsky description is a bit artificial, right?
Yes, I think so. Yes, it
uses
G vectors. Yes.
Exactly. Right. So there are all these. Work that are trying to use these kind of X-triangulated categories. Are you aware of this or?
X-triangulated category in the sense of Nakaoka Paru?
Yes.
Yes.
Yeah.
Yes, but
so yeah. maybe, I mean, the problem is that in more general algebras or finite-dimensional algebras or quiver algebras, this might not translate into a cluster setting, right? I mean, this is, but no, this is beautiful, really.
Yeah, but I think there's a work of Derksen and Fay, which interpret
Yes.
this invariant in terms of two-term injective complexes. And
Yeah.
according to their description, I think this definition of invariant is very natural.
Right. Yeah.
Yeah,
Yeah, exactly. Yeah. This
yeah,
has
yes,
been generalized lately by Schröer and Laverny Fragoso. They have taken into account the Zenfei work and
yes.
yeah. No, this is very nice. It's very, very nice. Congrats.
Yeah, thank you. Yes.
So, do we have any more questions, comments? Okay, then let's thank Professor Fujita again.
Thank you. Thank you so much.